have a couple of things to finish before we leave section 4. Alright, so we have a vector space V, and we assume F is a subset of V, and that is linearly independent. So if V is a vector in the vector space, and if V is not in S, alright? So we make sure V is not in S, then the union of the set S and the singleton. Singleton is just a term to denote a set consisting of only one element. If a set has no element, we call it an empty set, right? Empty set. So we know what's empty set because it's just a set and contains no element. A singleton is a set consists of only one element. So this is a singleton because it's a set consists of only one vector. Okay. Now, before I prove the theorem, let me make a remark. So, given an arbitrary vector space, we can use this theorem to construct the linearly independent set. How? Well, so step 1, we let S equal to the empty set. Okay, and first, our target is a linearly independent set, right? So at first we have nothing, so S is an empty set. Okay, there's nothing here. Step 2. Oh, by the way, I'm sorry. I spent. Sorry, I'm sorry. Alright, so V is not contained in the span of S. Then the span of S of the empty set is defined to be the trivial set reason. It consists of only one element, which is C. Right? So this is by definition because that we have to do something, right? So the procedure is that we haven't defined that before, right? So if somebody asks you, what is the span of an empty set? Well, it's not empty at all, okay? It's not empty at all, okay? It's a singleton. Very, very odd, right? But this definition is very useful. So I call it a definition, okay? Any of you against this definition? You can give me a reason. Maybe I will accept your reason and I will change my mind. Maybe. Yeah. Yes, please. Yeah. Because we usually say the span of a subset. Because the span of subset. Okay. What is the span of subset? Consists of all vectors which are linear combinations of elements in S. Okay. But for any set you have no element, pick up, right? How do you form linear combination? You don't have any vector. You don't. But I don't want it to be empty, so I just say, okay, just zero vector consists of the zero vectors. So that I can find it. So it's a set. The span of a set is also a set, that's of course. And did I answer? You can ask one more if you are not satisfied. Right. So the span of the empty set is defined to be the set, right, consistent of zero vectors. Okay, so it's a singlet. Okay, good. Now with that, so okay, so now we pick up any non-zero vector we want in V in space. So we pick up any non-zero vector. Then, of course, V1 is not in the span of S. Right? In this term, which is just the span of empty set, and which is there. Because V1 is non-zero, so of course it's not an element in this singleton, because this singleton consists of only zero vector. Alright, so that by the box theorem, and which is equal to V1. Okay. I.e. the current so we have V1 here. So now the set is not empty anymore because we have it consists, the set S consists of one non-zero vector. and which is linearly independent. Okay? Step 3. Step 3. If there is an element that is a vector V, right, in and V not in the span of S, then this union V become to a new a bigger linearly independent set. Right? And if also if the span of X equal to V that, right? Step 3 and continue. So the algorithm is like this one. That we start with the empty set. Okay. So sometimes we say an empty set is a linearly independent set. Okay, you can say so. Empty set. The empty set is a linearly independent, a special kind of linearly independent set. So we start with a spatial linear independence, which is the empty set. And the span, by definition, is the singleton, which consists of only the zero vector. Alright, so these new things are, these two concepts are new for you. Okay? I hope you remember. Just by definition. And it's reasonable because that with these definitions, you have no contradiction to the following development of the whole theory of linear algebra. Right? And then we start that. So the procedure is, the second thing is that you pick up an arbitrary non-linear vector, say V1. Okay. So just, and then we know that V1 is not in this singleton, not in the span of S. Okay, so from the previous theorem, that we can replace S by the union. So this union, so the current S is the set, just again the singleton, right? And which is linearly independent. And later on, we will do it again and again. So let's see. Suppose this is the vector space. And we pick up V1, okay, which is not equal to 0. Right? Pick up 1. Right? And then we form the span. So this is the span of V1. Right? So V1 span. And then we pick up something outside of the span. So we call it V2, right? Right? So this V1 and V2 together become a linear independent set. And so now, let me use different color. So now we have bigger span. So this is the span of V1, V2. That's bigger. And then we find out, oh, okay, the span of V1, V2 is not equal to V. So we are able to find V3 here. Okay? And now this time, the span of the V1, V2, V3, V1, V2, V3. It's bigger. Now it's bigger. But still, we have another outside. We have V4. Right? And finally, we find that with V4 together, we find that V is equal to, there's nothing left. V1, V2, V3, and then V4. And we stop. No further. Okay. So now, the conclusion is that now, so that S equal to V1, V2, V3, V4 is linearly independent subset of V. Okay? So we finish our procedure. Is that okay for you? Okay. But this procedure will be very useful later on, especially in chapter 5. Okay. Our further discussions. So, okay. Now I have to give a proof, right? The proof. So we prove this by contradiction. Okay, so suppose. So our strategy is to prove it by contradiction. So suppose that S union V, okay, is linearly dependent. Okay, so let's suppose that this is incorrect, right? Or yeah, we can say that it's actually the fact is that we are going to prove that if this is P, right? Before P, and the statement is Q. So we are going to prove P implies Q, but they are equivalent to not Q implies not P. So it's competitive. So we are going to prove. So suppose not Q. Not Q means that this state, this union, is linearly dependent, right? And we are going to show that we have not P. Not P means either V, not in V. It's impossible, right? Because every vector must be in our vector space. So only case space, the only not P is what? Is that V is in the space, right? So to prove not Q goes to not P means that if we assume, so we assume, maybe I assume that not Q, right? So the union is linearly dependent. I will prove that this V must be in the space. Alright? So you know my strategy, okay? Good. So now Now we assume this is linear independent. Right? So there exists U1, U2 up to UN, right, in the union, such that A1, A2 U2 plus AN UM equal to the zero vector for A1, A2 up to AM, not all 0. Okay? So we must have a non-trivial linear relation, right? This is the definition of linear independency. Okay? So there exists such a non-trivial linear relation in the union. Right? First of all, we must have UI equal to V for some I. Why? Otherwise, U1 U, U1, U2 up to UN are vectors in the set S. And the A1, U1 plus A2 plus AM, UM is non-trivial. Linear relation. Which is a contradiction. So the linear independence whether we say that S is linearly independent, so we don't have any non-trivial linear relation in S. We don't. Okay? So this is a contradiction. Otherwise, if all the U1 up to M in S, then you get a contradiction. So that's why some UI must equal to B. Okay. Next thing, we must have I put a verb here. So we must have AI not equal to 0. So, oh, sorry, I forgot to turn up. Okay. So the first we already know that sum of the ui is equal to b. The second thing is that the corresponding coefficient must be non-zero. Okay, it must be non-zero. Okay, otherwise u1 a1 plus ai minus 1 ui minus 1 plus ai plus 1 ui plus 1 plus am equal to 0. Okay. It's a non-trivial linear relation in S. Okay. Again, it's a non-trivial linear relation. Because if AI is 0, then you can neglect from this linear relation, right? And so sum of the coefficients, a1 up to ai minus 1, ai plus 1 up to am, some of them must be non-zero, and u1, u up, u sub I minus 1, u sub I plus 1, etc. up to um must be in S. So this is a non-trivial linear relation in S. Okay, a contradiction again. Any questions? Yes, please. Because when we say S is linearly independent, means that we don't have any non-trivial linear relations in S. That's the definition. You shouldn't have any non-trivial linear relations. Because once you have a non-trivial linear relation in S, then this S is linearly independent. So you can't have any non-trivial linear relations. That's the definition. Say that. And so yeah, you can see when I say that this is a linearly dependent set, I say that we have a non-trivial linear relations in this set, in this union. So that u1, u2, and um can be elements in S or can be equal to B. Okay. And the coefficient cannot be all 0. Such a linear relation is called non-trivial linear relation. And first of all, we know V should appear here. If we have such a non-trivial linear relation, then V should appear here. If not, then all these elements are from S. And then this non-trivial linear relation will be a non-trivial linear relation in S, and which is a contradiction. And second thing is that we know ui is equal to 3, right? Now the corresponding coefficient ai must be non-zero. Because if ai is 0, then the non-trivial linear relation becomes true this one. And this is a non-trivial linear relation in S because all the vectors are from S. Okay? So that we have no way to go, right? So now, finally, now we have AI U equal to A1 U1 minus A2 AI minus 1 UI minus 1 AI plus 1 UI plus 1 minus AM UI. so V becomes to a linear combination So it comes to a linear combination of elements in S. Okay, so it's in the span of S. Right, so we complete the proof. So we start with not Q. This is not Q. Okay, so we start with. This is not Q. And we go to, this is not T. So we finish the proof. Any questions? Yes. Yes. Yeah, I can't really understand your question. Otherwise, means if U are not equal to B, if none of the M vector is Vi, is V, then U1, U2, and UM are, they are in S, right? They must be in S. So this is become to a non-trivial linear relation in S, solely in S. Because now U1 is not in V, U2 is not, okay, U1 is not equal to V, U2 is not equal to V, etc. up to UM is not equal to V. Right? And so U1, U2 up to UM must be in S, right? So this is a non-trivial linear relation in S. Then that means that S is linearly dependent. But it's a contradiction to our assumption here. S is linearly independent. So that's why I said otherwise. Otherwise means that if this is not the case, right? This is statement when we call it R. Right? Now what is not R? Not R means UI not equal to V for all R. Logically, right? For some I means that there is some I such as UI into V. And the nut of this statement is that UI not equal to V for all I. This is called otherwise. Otherwise means not equal. We are in not R, then we have this consequences. And it is a condition. Okay? It's the logic. It's a way to write the English. Maybe I can write another way. Okay, next time I avoid to use otherwise. Maybe I can turn it around. So are you satisfied with my explanation? Okay. And this is the same reason here. So even though, so now we know some say some I, we have ui equal to v. And then for that I, the AI must be non-zero. This way. Alright? Because if AI is 0, this is again, right? Otherwise, means if this is not the case, then we have AI equal to 0. When AI equal to 0, this relationship can be written this way because the ith term is 0, right? So we just take it out. Because 0 times v is 0 vector. So that this non-trivial linear relation becomes shorter and only have m minus 1 terms. Because the ith term is, can be removed because it's 0 vector. It's a 0 vector. So I remove the ith term. For example, if I is 1, okay? If I is 1, so U1 is equal to V, suppose that. U1 is equal to V. Then if AI equal to 0, so that this is here. Okay, so the rest of the UIs are in S. So it comes to linear relation. Right. So the only case is that we have this situation. So UI is V and the AI is not 0, so I can write down this way and I can divide. Because AI is non-zero, so I can do the division. So I can express V as a linear combination of elements in S. And so I finish the proof. Okay, so definition. So we take V and W in two vector spaces over them R. That just indicate they have the same set of coefficients. They are coefficients. All their scalars are from the set of all real numbers. Okay, and a function T from V to W. When I say that function from V to W, so its domain is V and its codomain is W. So a function is called linear if T alpha U without V equal to alpha beta T3 for all UV V and what is that? Or sometimes maybe I write it called linear transformation. From V to W. Maybe I write it in this way. So this definition is very similar to our previous versions when we consider functions from Rn to Rm. Okay? And value corresponding from Rn to Rm, then we write down the same formula. Okay, and the U and V are in Rn. So that it just says that this function will map a linear combination of two vectors in the domain into similar linear combinations, all right, in the codomain, and the coefficients remain the same, but in the codomain we will use the image of the value of the U, the vector U here, and the image of the vector V in the domain. So basically, you have the same property, but now we just extend to any functions from a vector space into a vector space. We just generalize the idea of linear transformation. Okay. So so you can think about everything about linear transformation from Rn to Rm. Okay, because the behavior is quite simple. Any questions about the decision? Okay. So a theorem so let B be a linear transformation from a vector space V to a vector space if S is a linearly dependent state. In the domain, then the image of S is also linearly I should be careful. Yeah, I think I should be very careful. Because there is some trap here. Let me address the theorem carefully. Right. So I will tell you where is the trap. If the index one up to UN is linearly dependent in V, right? So you know what is index? Just I index the vectors. The index is index. So it's possible U1 is equal to U2, right? It's possible, okay? So whenever I say index set, it's possible some of them are the same vectors. Now, so the index set is linearly dependent in V. Right? Then the index set T1 we this is T1 0, this is T2, etc. Wn, which is Tn. Now the index set is also linearly independent, not linearly dependent, it's also linearly dependent in W. So I have to consider index. And before I prove that, I give you why I have to consider index. Alright, so let me take an example. Alright, so okay. Projection. Okay. Maybe I'll take that later. I prove that first. Okay, I prove that first. The index set U1 U2 up to M is linearly dependent in V, you can only that is A1 into and not all zeros, right? Such that A1, B1, A2, B2, up to AM, QM equal to 0. So we have a non-trivial linear relation, right? In this index set. So now we take the okay, take 0, yeah. So we take the linear transformation T. But this one, we know this is T, 0 times 0 vector. So this is 0 times T, 0, so this is 0. Okay. I just proved that for any linear transformation, because we have already proved that before for for all linear transformation from Rn to Rm, right? To say that T0 goes to 0. So actually, a zero vector in B after linear transformation will go to the zero vector in W. That's always true. But I haven't proved that, right? Okay, so I have to prove here. But actually, we have done a lot about the linear transformation from Rn to Rm. All this property can be transferred to arbitrary linear transformation from a vector space B to another vector space W. Okay, but of course we have to prove that, right? Because this is a new concept. It's a generalization. So I just say this is 0. How about that? This is the bilinearity, right? So we have T U1. Okay. So now, and so because we write it, this is we define this as W1, and we define this as W2, and we define this as Wm. So we have A1, W1, plus A2, W, plus AM, Wm equal to 0. Okay, so which is a non-trivial linear relation in the index set. Okay, in the index set. So that's the index set. Index set B U1, B U2, up to T M is linearly dependent in W. So, and the proof. All right, from the proof, I will show you that it is possible if we don't use the index set, the concept. Suppose we just think about this as set. So any repeated, if we have say W1 equal to W2, it is possible U1 and U2 are different, but they have the same image, right? They have the same image. So W1 may be W2 equal to W2, right? And then we have to remove one, right? As a set. We cannot have a repeated element. But for an index set, we can have the same element. That takes the difference. So it's possible that even though, for example, we have 100 and U here, all right? But after the image, you may have only 2 or 3 different images here. But these 3 images could be linearly independent because it's a small set. Okay, here this is a small set. Okay, so be careful. When you want to do this, we have to use the index set. Okay. So from here, you know, in the exercise I assigned to you, that even though you have a linearly independent index set, the image may not be linearly independent. Why? Because they have repeat. They may have the same images. Okay. So if the index set is linearly independent, the image may not be linearly independent. Okay. But the theorem says that if the index set is linearly dependent, then the images must be linearly dependent. Okay. So let's take a 5 minutes break. Okay, so I finished section 3.1. Alright, so big space. I think I have to reverse the word. Because I didn't fit. I'm sorry. Okay, matrix inverses. Because that section is 3.1 about multiplication matrices, non-commutativity of the multiplication of matrices, or associativity of matrices. So that we have discussed a lot about this. But you can read through the whole section without any difficulty. Right? So now I want to jump to the second section. Alright. And this is the coverage for our first meeting. Okay, so next week. Alright, so definition. Okay, so let A be be M times N, right, matrix, and B and M times N matrix. Right, so we have two matrices. A, the dimension is M times N, so A has M rows and N columns. But on the other hand, the B matrix has sorry. The B matrix has N rows, but M columns. Right, if A times B equals the identity, so what is the dimension of the identity? Must be M times N, right? So if A times B equal to the identity matrix, so I have to, because it's a definition, right? So when this is true, A is called left inverse of B, and B is called right inverse of A. Okay, so rectangular matrix may have inverse, but I'm talking about the left inverse, right inverse. Okay. So that if I have this equation, A matrix times B matrix equal to the any matrix, then to B here, A is called a left inverse because you multiply B from the left side. And on the contrary, B is called the right inverse of A because you multiply A by B from the right hand side. So this is the definition. Okay. So example. Okay, so let me see. I have a quick example here. I do have one. So let me see. Okay. So let's say A is equal to 1, 2, 2, 5, 1. B is okay. That is 1. And so this A is 2 times 3. B is 3 times 2. Now you multiply AB. So this is and you find out when you do the multiplication. Okay. So you have 1 here, and this is 0. This is 0. Okay. So this is the identity matrix. So A is the right inverse of B. So this the chemical matrix A is the right inverse of B, and this matrix is the okay. A is the left inverse of B, and B is the right inverse of B. So let me consider a linear system. Ax equals b. Right? First of all, we consider a linear system. If A is a right inverse B, then this linear system has at least one solution. B and then you can immediately write down the solution. The proof is simple. So when you consider a linear system like this one, and when you know that the coefficient matrix A has a right inverse B, then this linear system has at least one solution. It means that it is consistent. And such a solution can be found to be B multiplied with And the technique is very simple, right? Because that with right, we have equal to and this line associativity identity. Okay? So it's quite simple. So the information about right inverse is so useful because that you can find out the now. Oh, time's up. Alright, so I have started.